Hello, thanks for joining this physical science session. We're going to talk about electricity in section 6.4, looking at properties of circuits. So we know that we have series and parallel circuits, and the difference between them is that with a series circuit, the electricity goes in order from one device to the next, and it only has one path along which the current can flow. Whereas with a parallel circuit, um, it's got multiple paths that the current can flow on at the same time. So we're going to look at some aspects of series circuits first, and then we'll go do parallel. So first is resistance in a series circuit, and it's actually very simple. You just add together the resistance of each individual resistor. So we have this little circuit that has three resistors. It has a 5 ohm light bulb, a 10 ohm squiggly resistor, and a 5 ohm light bulb. So we just add them together. 5, 10, and 5 gives us 20. So that is all you have to do to find the resistance of a series circuit. And current in a series circuit is using the formula that we got in the last section. Current equals voltage divided by resistance. If you're only solving for the current of one part, you just use the resistance of that part. So you've got different resistors, so you might want to find the current in one resistor, so just use that. But if you're looking at the current for the entire circuit, you have to add up all of the resistances to find the resistance of the entire circuit. So use the voltage of the whole circuit divided by the resistance of the whole circuit. So it looks like this. If this is our circuit, our voltage is 48, and our resistance for the whole circuit is the total of the two devices that we have. So 18 plus 6. So our resistance is going to be 24. So your voltage is 48, resistance is 24. So now we have those two numbers. We can put it back into our formula here. Our voltage is 48, our resistance is 24, and so our current is 2 amps, 48 divided by 24. Okay, so it's not too bad. Sometimes you'll be given the resistance, but more often than not, you'll get a thing like this where it says, well, you have a few resistors, you have to add them up to find the total resistance. Now, voltage drop is the change in voltage across any device that has resistance. So you have a voltage that is shown on the battery or the generator, and that's the overall voltage for the whole circuit. And as it goes across each light bulb or squiggly resistor or any other resistor, it's going to show a voltage drop. So that voltage will change as it goes across each one. So for example, you've got this same circuit here that we just looked at. We start out with 48 volts over here. As it goes across device 1, which has a resistance, the voltage is going to decrease, so it won't be 48 anymore. And then it'll be a different number here, in between device 1 and 2. And then it's going to drop again across device 2. And so to figure that out, we just use our standard voltage formula where voltage is current times resistance, and we just use the resistance of that particular device. So in this case, we know the current is 2 amps because it tells us that. And if we're looking at device 1, we say the voltage is current times resistance. So it's 2 amps across the device 1, so 18 ohms is the resistance. So the voltage drop there is 36. Okay, so it loses 36 volts as it goes across that. And then device 2 is going to be 2 amps times 6 ohms, and that gives us a voltage drop of 12. So we had 6 ohms here, our current is still 2 amps, so voltage drop is 12. And the beauty of it is that the voltage drop of the whole circuit is equal to the voltage drop of adding up all the ones that you have. So over here, it starts with 48 volts, and then we lose 36 volts, we lose 12 volts, so over here, it's actually 0 volts, because we've lost all 48 of them. So that's a way to check your work. Your voltage drops of each resistance should add up to the total voltage drop of the whole circuit so that you end up starting out with however much it tells you and ending up with 0. And we're just going to do another example of the same thing here, another example of voltage drop. So we have this little circuit. It's got 2 resistors on it. Its current is 3 amps. So we're going to look at the voltage drop across the light bulb. So the light bulb is 5 ohms. The current is 3 amps. So 3 times 5 gives us a voltage drop of 15. Okay, so it loses 15. So we started out with 45. It's lost 15, so now it's 30 volts on the other side of this light bulb. Okay, because it lost 15. And then across that squiggly resistor, our amps is still 3. Okay, that's still our current. We have 10 ohms, right? Over here it says 10 ohms, so we have 3 times 10, and that gives us 30. So it loses 30 volts. So it only had 30 volts. And then over this resistor, it loses 30 volts. So now our voltage is 0. Okay, so that's good. It lost the entire voltage by the time it gets back to the battery. So we've got some practice questions on series circuits. They're all kind of crammed into one slide because they go together. So we've got a series circuit contains an electric generator, 3 devices operated by electricity in the wires. Okay, their 3 devices have 3 resistances, 20 ohms, 8 ohms, and 4 ohms. So what is the total resistance of the circuit? So remember, for series circuits, resistance is easy. You just add them all up. So we have 20 plus 8 plus 4, 32 ohms. Okay. Next question is talking about the same circuit. If the terminal voltage is 110 volts, what current will flow through the circuit? Okay, so this is also pretty simple. We just use our formula for current, which is current equals voltage divided by resistance. And we know the voltage is 110 because it just told us that. We figured out that the resistance is 32. So 110 divided by 32 gives us our answer, 3.44 amps. And our third question is going to be about voltage drop. So what will be the voltage drop of the device having a resistance of 8 ohms? So with voltage drop, we need to know the amps, which we found out, and the resistance. Now, just remember, we're talking about just the resistance of one part. Okay, so we have our current for the whole circuit, but we're talking about the voltage drop just across this device, 8 ohms. So we don't want to use the number that we found for the resistance of the whole circuit. We're not going to use that because we're not talking about the whole circuit. We're talking about how much the voltage drops just in that one spot. So voltage is current, which is 3.44 times resistance of that device, which is 8. 3.44 times 8 gives us 27.52 volts. Okay, parallel circuits are a little trickier in most regards. So resistance is different with a parallel circuit. What's really strange and interesting is the total resistance is less than the resistance of any individual part of the circuit. So we have the circuit with these 3 resistors. We have a 5, a 10, and a 5 ohm resistance. So when we do the math and figure out the resistance of the entire circuit, it's going to be less than 5 ohms. Okay, so that's a way to kind of check your math and make sure you're on the right track. Or it will be less than any individual part, so less than 5 ohms. So the formula that we have for solving for the resistance of a parallel circuit is 1 over the total resistance. Okay, that's 1 over R. R on that side is the total resistance, equals 1 over the resistance of device 1 plus 1 over the resistance of device 2 plus 1 over the resistance of device 3. And you could keep going for how many devices you have. So if you have 12 devices, you just keep going 1 over resistance, 1 over resistance, 1 over resistance 12 times. Okay, and that's what I said here. The amount of times that you're seeing 1 over R depends on the number of parts being measured. So let's just stick with this for this example that only has 3 resistors. So our formula is going to be 1 over the total resistance, and this is what you're solving for, is this R here on the left. Okay, just total resistance. It doesn't have a little subscript number, it's just overall resistance. And we're going to add 1 over the resistance of the light bulb, 1 over the resistance of the squiggly resistor, and then 1 over the resistance of the other light bulb. So we have 1 over 5, 1 over 10, 1 over 5. And then I like to just turn those into decimals to make life easier. If you're good at adding fractions, you can do that, but I just took 1 over 5 and got 0.2, 1 divided by 10 and got 0.1, and 1 divided by 5 and got 0.2. So now we have our formula is 1 over the total resistance is equal to 0.2 plus 0.1 plus 0.2. So we add those together, 1 over total resistance is 0.5. Now some people are tempted to stop here, but you didn't solve the problem. Okay, 0.5 is not your answer. 0.5 is only equal to 1 over the resistance. We got to get this resistance, this R, all by itself. Okay, so we've got to do a little bit of algebra here. 1 over resistance is 0.5, so if we multiply both sides by R, we get 1 is equal to 0.5 times R. And now we still need to get R by itself, so we take both sides of the formula divided by 0.5, and we get 1 divided by 0.5 equals R. And our final answer, if we take 1 divided by 0.5, we get 2. So our final answer is 2 ohms. And just to check to make sure we're on the right track, this should be less than any of the individual resistors, and it is. Our lowest one is 5. So our answer is less than 5 ohms, so that's probably good. Okay, we'll do a practice problem in that in a minute, but first I want to go over current in parallel circuits. So with a series circuit, your current just has one path to go on, so all the current stays on one path. With a parallel circuit, that's not how it is. So if we start out with 5 amps, but then we have parallel branches, what happens? Well, that 5 amps has to split up between the other 3 branches. So you got your 5, but it splits up, and then it comes back together when it goes around the voltage. And what's important is that it's the same amount of current, it's just split. So your your 3 branches here have to add up to the 5 amps that you started with. Okay, the sum of the current in all of the parallel paths has to be equal to the current when it only has one path. So you started out with 5, so when it splits up into these different paths, we still have to have 5. So we have 2 plus 1 plus 2, and that still gives us 5. So we didn't lose any current. So here's a practice question for parallel circuits. So we have this circuit with 3 parallel resistors, 20 and 8 and 4. So what is the resistance for them? Well, here's our formula. 1 over the total resistance is equal to 1 over the resistance of number 1, and 1 over the resistance of 2, and 1 over the resistance of number 3. And we just put our numbers in for that. So 1 over 20, 1 over 8, and 1 over 4, because that's our 3 resistors here. So remember, this on the left is what we're solving for. We're trying to find the total resistance of the whole circuit, and we're using the 3 resistances of our 3 resistors. So 1 over 20 plus 1 over 8 plus 1 over 4 is going to give us 0.425. And we're not done yet because that is not the total resistance. 0.425 is equal to 1 over the total resistance. So we do some algebra. We're multiplying both sides by R, and we get 1 equals R times 0.425. Then we divide both sides by 0.425 because we want to get R all by itself. So 1 over 0.425 equals R, and if we divide that, 1 divided by 0.425, we got our final answer of 2.35. Okay, so finding the resistance of a parallel circuit is a little more complicated than a series circuit, but as long as you stick to that formula, you'll be okay. Now, using that same circuit, assume that voltage is 110 volts, and we figured out in the last problem that the resistance is 2.35 ohms. So our question is, what current will flow through the wires between the generator and the group of 3 devices? So over here, where it's not splitting up yet, we've just got a current. So all we have to do, current is equal to voltage divided by resistance. Our voltage is 110. We figured out in the last problem our resistance is 2.35. So 110 divided by 2.35 gives us 46.8. And our last question with this diagram, what portion of the total current will flow through the device that has a resistance of 8 ohms? So over here, our current is 46.8. But that gets divided as it goes through these. So our current is split 3 ways. It's split between these 3 devices. So how much is going through that device with the resistance of 8 ohms, this one in the middle? Well, in general, our formula for current is current equals voltage divided by resistance. So we know our voltage is 110. And resistance, we're just talking about this device, so we're going to use this 8 ohms resistance. So 110 divided by 8 is going to give us our answer of 13.8 amps. And that's it for that reading section. And there's only one type of practice problem in the next one, the magnetic effects of current. So we're just going to go over that real quick too. And this is about transformers. So you have an input voltage, and then you have 2 sections where you have wire wound around them. So you have the primary first, and then the secondary, and then you have the output. In this case, it's just showing it's running a device. It's running a light bulb. So, when you have a step-up transformer, it looks like this, where the number of times it's wound around the primary is less than the number of times it's wound around the secondary. So as it goes from primary to secondary, the number of windings increases, and so the voltage also increases. You'd have a step-down transformer where you start with a lot of windings and you have less. So as the number of windings decreases from primary to secondary, the amount of voltage also decreases. And we could calculate the exact amount of the voltage change by using this formula. The primary voltage divided by the secondary voltage is equal to the number of turns in the primary divided by the number of turns in the secondary. So as long as you know 3 of those numbers, you can figure out the 4th one. So let's just look at one quick practice problem. A transformer has 60 turns in the primary and 90 turns in the secondary. If the primary voltage is 250, what is the secondary voltage? So our primary has 60 and our secondary is 90. So our number of turns is increasing. That means our voltage is going to increase too. So let's do the math and figure out how much. So our primary voltage divided by our secondary voltage is equal to the number of turns in primary divided by number of turns in secondary. So our number of turns, it gives us the beginning, 60 turns in the primary, so that goes there, 90 turns in the secondary, so that goes there, and the primary voltage is 250, and we don't know the secondary voltage yet, that's what we're looking for. And so now we have 3 of those numbers, and we could just solve for the 4th one. So the easiest way to do it is to cross multiply. You take 250 times 90, and that's equal to the secondary times 60. And then you're going to end up solving for the secondary and getting 375 volts. And that brings us to the end of this session. We definitely didn't go over everything that's in this reading section. There's a lot more to go over, so read it and watch the other practice videos and do your practice problems. But if you do have any other questions, don't hesitate to contact your instructor.